Hello everyone. I am Yu Hao Qing from the University of Hong Kong. I will present our work, Neuron Sensitivity Guide Test Case Selection to you. This is collaborative work done by researchers from the University of Hong Kong, Shanghai Jiao Tong University, Singapore Management University and Tianjin University. Deep neural networks, or DNNs, have been widely deployed in software to address various tasks, such as autonomous driving, medical diagnosis, and machine translation. The significant performance of DNN-driven software has substantially changed our daily lives. However, like traditional software driven by deep neural networks is also susceptible to defects, which can lead to accidents in autonomous vehicles or erroneous medical diagnoses, causing economic losses and safety risks. Therefore, there is an urgent need to develop and apply effective quality assurance techniques to DNN-driven software to ensure its reliability and safety. Ensuring the quality of DNN-driven software is a complex issue due to the differences between DNN models and conventional software systems. Unlike traditional software that relies on developers manually constructing the logic flow, DNNs are constructed based on a data-driven programming paradigm. Sufficient test data is critical to detect and repair incorrect behaviors of DNN-driven software. This requires DNN developers to collect a significant amount of data from various scenarios and hire a large workforce to label it, which is highly expensive and time-consuming. Identifying and selecting the most valuable and representative data, which are fault-inducing inputs that DNNs will misclassify, becomes critical for improving the effectiveness and efficiency of DNN testing. Prior researchers proposed using neuron coverage to measure the adequacy of DNN testing, inspired by the success of code coverage criteria in conventional software testing. Two notable examples are neuron activation coverage, or NAC, and K-multisection neuron coverage, or KMNC. NAC, proposed by DeepExplore, considers a neuron covered if its activation exceeds a certain threshold. KMNC, on the other hand, divides each neuron's activation range into multiple segments. If a test case's activation value falls within one of these segments, that segment is considered covered. Based on these coverage criteria, researchers have developed coverage-guided test case selection methods to identify valuable tests from candidate datasets. However, the effectiveness of these methods has been questioned, as studies have shown that increased neuron coverage does not necessarily correlate with a higher fault detection rate, or FDR, which is the ratio of misclassified cases among selected cases. Moreover, collecting neuron coverage is computationally expensive, making it challenging to apply to large-scale models and datasets. This overhead limits the practicality of neuron coverage-guided test case selection in real-world scenarios. To address the problems of neuron coverage-guided methods, recent researchers have proposed uncertainty-based prioritization techniques. These techniques prioritize test cases based on rules applied to the final layer outputs of DNNs, such as vanilla softmax, softmax entropy, prediction confidence score, Monte Carlo dropout, etc. For example, DeepGenie prioritizes test inputs that are predicted with more similar probabilities for all classes. By prioritizing inputs with higher uncertainty, these approaches aim to uncover inputs that are most informative for model improvement. However, relying on final layer outputs may not accurately reflect internal neuron behaviors and limits visibility for DNN developers. In many cases, developers need to understand the internal logic of the DNN model to effectively optimize and debug it. To utilize internal neuron information for test prioritization, we propose Neuron Sensitivity Guided Test Case Selection, NSS. Neuron sensitivity measures the change in a neuron's output for small input perturbations. We observe that a test case with high sensitivity values for a neuron is more likely to cause the model to produce incorrect behavior. To prioritize test cases with neuron sensitivity, we propose 1. A test case's neuron sensitivity score, TNS score. 2. A sensitive neuron identifier to efficiently identify the most sensitive neurons. 3. A method for prioritizing test cases based on their TNS scores calculated on the sensitive neurons. We define the test case's neuron sensitivity score to measure a test case's impact on a DNN. Given a test case X and a set of internal neurons in a DNN, the TNS score of X is defined as the sum of the neuron sensitivity values across all neurons. To calculate it, we feed the test case into the DNN to get the neuron activation values, and apply a benign mutation to the test case to generate a mutated version X, and then calculate the difference in activation values between the original and mutated test case for each neuron. Finally, sum the differences to get the TNSS score for the test case. A higher TNSS score indicates the test case is more likely to cause incorrect DNN behavior. Calculating TNSS scores with all neurons can be computationally expensive for large DNNs. To address this challenge, we propose the sensitive neuron identifier. This technique efficiently identifies the most sensitive subset of neurons in a given DNN that contribute the most to the model's output. As shown in Algorithm 1, the sensitive neuron identifier takes the following key steps. First, it randomly samples a small subset, such as 10%, of the original test cases. This allows it to estimate neuron sensitivity patterns from a representative subset, saving significant computation. Next, for each test case in this subset, it generates a mutated version by applying a random benign transformation like rotation or scaling. It then feeds both the original and mutated samples into the DNN. The algorithm calculates the neuron sensitivity, defined as the absolute difference in each neuron's activation values between the original and mutated samples. It accumulates these sensitivity scores for each neuron across the subset. Finally, it identifies the top K% of neurons with the highest accumulated sensitivity. These are deemed the most sensitive neurons that are critical to the DNN's predictions and are prioritized for the test case selection. By focusing only on this sensitive subset of neurons, the sensitive neuron identifier allows NSS to efficiently calculate TNSS scores and select valuable test cases, even for very large DNNs, while maintaining high effectiveness. Now that we have defined the test case neuron sensitivity score, or TNS score, and identified the sensitive neurons using our sensitive neuron identifier algorithm, we can effectively prioritize the test cases that are most likely to cause the DNN to fail. The prioritization process works as follows. First, we use the sensitive neuron identifier to detect the sensitive neurons in the DNN. Then, for each test case in the candidate set, we apply a benign mutation, such as rotation or scaling, to generate a slightly modified version of the test case. We feed both the original test case and its mutated counterpart into the DNN. Next, we calculate the TNSS score for each test case, but importantly, we only consider the activation values of the sensitive neurons that we identified earlier. By focusing on these critical neurons, we can efficiently assess the impact of each test case on the DNN's behavior. Finally, we select the test cases that have the highest TNS scores. These are the test cases that are most likely to expose incorrect or unexpected behavior in the DNN. By prioritizing these high TNS score test cases, we can effectively allocate our testing and retraining efforts to the most valuable and informative samples, thereby improving the efficiency and effectiveness of our DNN quality assurance process. In our evaluation, we assess the performance of NSS on 4 widely used datasets: MNIST, SciFAR-10, SciFAR-100, and Fashion MNIST. We also consider 4 representative DNN models: LeNet1, LeNet5, ResNet20, and VGG16. To benchmark NSS against existing approaches, we compare it with 3 categories of baseline test selection strategies. The first category includes neuron coverage-based methods, which prioritize test cases based on their ability to activate different neurons in the DNN. The second category consists of surprise adequacy-based methods, which aim to select test cases that are most dissimilar from the training data. The third category encompasses uncertainty-based methods, which focus on test cases that the DNN is least confident about. We evaluate the effectiveness of NSS and the baseline methods using 2 key metrics. The first metric is the fault detection rate, or FDR, which measures the proportion of selected test cases that expose incorrect DNN behavior. The second metric is the model accuracy improvement achieved by retraining the DNN with the selected test cases. To generate a diverse and representative set of unlabeled candidate datasets for test case selection, we employ 7 different mutation strategies. These strategies apply various transformations to the original test cases, such as rotation, scaling, and adding noise, to create new test cases that mimic real-world variations. We analyze the correlation between a test case's TNSS score and the model accuracy on that test case. the results show that TNSS score is strongly negatively correlated with model accuracy across all dataset model combinations. Test cases with higher TNSS scores tend to have lower model accuracy, indicating they are more likely to cause the model to fail. For example, the Pearson correlation between TNSS score and accuracy is 0.993 for MNIST with LeNet1. NSS achieves a higher fault detection rate compared to the baseline selection strategies in most experiments. For example, when selecting 5% of the test cases for MNIST with LeNet1, NSS obtains an 81.8% FDR, while the best baseline only obtains 64.7%. NSS is able to detect more diverse types of error-inducing inputs compared to the baselines. We measure diversity using the ratio of area under the curve, RAUC, of cumulative unique fault types detected. For example, when selecting 20% of test cases for MNIST with LeNet1, NSS achieves an 88.99% RAUC, while the baselines only reach 85%. The test cases selected by NSS lead to significantly higher accuracy improvements after retraining the models, compared to the baselines. For example, fine-tuning LeNet1 on MNIST, with the top 5% of test cases selected by NSS increases accuracy by 9.01%, while the baselines only achieve up to 7.57% improvement. The sensitive neuron identifier enables NSS to be much more efficient by reducing the number of neurons used in the TNSS score calculations. For example, on MNIST with LeNet1, using the sensitive neuron identifier decreases the runtime from 382.74 seconds to just 42.38 seconds. In summary, we propose NSS, a novel approach to efficiently select the most valuable test cases for DNN testing and retraining. NSS introduces TNSS score to quantify test cases' fault-inducing likelihood, the sensitive neuron identifier to focus on critical neurons and reduce overhead, and a neuron sensitivity-based prioritization strategy. Extensive experiments demonstrate NSS's superior performance over state-of-the-art baselines, with higher fault detection rates, more diverse error-inducing inputs, and greater model accuracy improvements after retraining. NSS provides an effective and efficient approach to enhance DNN quality assurance by strategically selecting the most valuable test cases. That brings me to the end of my talk. Thank you for your attention.